So Jai Jagannath. So today is the last application of the Gauss law we will discuss. In the last class, I had discussed some application of Gauss law. So today we will discuss the another application. Let us see. So this is your lecture number 4. Lecture number 4 of Gauss law, that is chapter 22. So let us take an example. So we have to find the example 22.7. So in this example, what we'll do, we have to find the electric field intensity due to a thin infinite uniform sheet of a uniform surface charge density of sigma. So let us take first positive plate, then we will discuss for negative plate. Okay, so now see, suppose we will take an infinite plate. So this is an infinite plate. So that is a bigger plate. Let us say the charge on this plate is equal to positive, and this plate is uniformly distributed. So since the total charge is distributed uniformly over the surface, we can say here there is a surface, so surface charge density will come into picture. So what is surface charge density? You know, if the total charge given to the plate is Q, the total area of the plate is A, then total charge distributed per unit area is called surface charge density. What is the unit? So charge is in coulomb, area is in meter square. So this is the surface charge density. So what we will find? We will apply Gauss law to find electric field intensity. Let us say this is a point P, and this P point is just in front of this charge sheet. And what is the charge density? Charge density is sigma. So what we'll do, we have to find electric field intensity at P. So we have to find electric field intensity at P using which law? Using Gauss law. So I have already told you that, so when you will apply the Gauss law, we have to take an imaginary surface, and that imaginary surface is our Gaussian surface. So in this case, we will select a Gaussian surface, which is nothing but a cylinder. So now take a cylinder, closed cylinder, which is passing through this P point. So now let us say this cylinder is passing through this plate, and I have taken like this. Okay, suppose the area of this cylinder, that is base area and top area, is A. And what is the area vector? Area vector is always perpendicular to the surface, and it is always outward. So if I will take, this is the Gaussian cylinder, here the area vector is away from the surface and normal to the surface. So let us say this is surface area 1, this is surface area 2. And I have already told you that in a cylinder there are 3 surfaces, top and base, which is circular, and last one is your third surface is your curved surface. So here, if I will take a small element on the third surface, the area vector is perpendicular to the surface. Let us say this small area is equal to dA. So here this is the area vector of this small element. Okay. So now what we'll do, I have to find total flux through this Gaussian surface. So what is the total flux? So total flux from this Gaussian cylinder is nothing but flux through this first surface, let us say this is phi 1, and flux through the second surface, let us say it is phi 2, and flux through the curved surface, let us say it is phi 3. Okay, so what is phi 1? You see, this one surface is at, say, each element on this surface is equidistant from this charge plate. So everywhere electric field intensity is constant. So we know for uniform electric field intensity, what is the flux? So flux is nothing but simply E dot area. So let us say this area of this cylinder is A. So this is the A. So now similarly, what is the flux through the second surface? It is E dot area vector plus what is flux through this small element? So from this small element, the flux is equal to E dot dA. But I want to find flux to the whole curved surface. In that case, I have to take the surface integral. The next question may come. So why you have taken electric flux is equal to here E dot A, but here why you are taking the surface integral of E dot dA? So because in the third surface, each point is at different distance from the charge sheet. So electric field intensity at each point on the curved surface is different. So E is non-uniform. So for non-uniform, you have to find the flux by closed integral of E dot dA. I think it is clear. So now see. So here at this P point, what is the direction of electric field intensity? So this is the positive charge plate. So I have already told electric field intensity is always away from the positive charge plate. So here this is the electric field intensity vector E. So E and A are in same direction. So what is the angle between E and A? That is 0 degree. So E dot A is nothing but EA cos 0. Similarly, here this is the point. I have to find the electric field intensity. This is the positive plate. So due to positive plate, electric field intensity is away from it. So here electric field and area vector are in same direction. So theta is equal to 0. So here for second surface, the flux is equal to EA cos 0. But what about the third surface? So here you see the electric field intensity at this point is away from the plate. So this is your E and this is dA. So what is the angle between E and dA? That is 90 degree. So I can write here it is surface integral of E dA cos 90. So cos 90 is 0. So this third part of this term is equal to 0. Okay, that means flux to the curved surface due to this charge plate is equal to 0. So that implied EA cos 0 is 1, EA plus EA, that is 2 times E into A is equal to total flux. So we calculated this flux using which law? Using mathematical expression of the flux. But as per Gauss law, what is Gauss law? As per Gauss law, that is the total flux coming out of this Gaussian surface is nothing but the total charge enclosed by the cylinder divided by epsilon naught. Okay, so let me take the practical example. You see, suppose this is the charge sheet. Okay, I want to find the electric field intensity in front of this charge sheet. So what I will do? I will take the Gaussian cylinder. Let us say this is my Gaussian cylinder. So I just penetrate this charge plate. Okay. So now tell me what is the flux through this Gaussian cylinder. So outside to this plate there is no charge, and the left side to this plate there is no charge. So what is the charge inside the cylinder? The charge is equal to charge of this surface area of this plate. So what is the surface area of this plate? So which is penetrated by the cylinder. So this is also A, because this area is A. So this area, that is, you see, this area is also A. Now we have to find what is the flux through this small flux through this area. So you know what is sigma? Sigma is charge per unit area. So charge per unit area is sigma. So per unit area, charge is sigma. Per A area, what is the charge? So charge is equal to sigma into A. So this sigma into A is equal to charge enclosed by this cylinder. Okay. So now as per Gauss law, we know the total flux is equal to Q enclosure divided by epsilon naught. But we had already calculated the total flux is equal to 2 times E into A. And what is the charge enclosed by the Gaussian cylinder? Sigma into A. divided by epsilon naught. So this A cancel. So we will get sigma. So we will get the electric field intensity in front of this charged sheet is equal to sigma upon 2 epsilon naught. So this is the expression, this is the derivation of electric field intensity at a point which is in front of a charged sheet. Okay. Now you see, the interesting point is that the point, so here in this expression E is equal to sigma by 2 epsilon naught. Sigma is the charge density of the plate, that is constant. 2 is constant, epsilon naught is constant. So electric field intensity is constant in front of a charge sheet, and electric field intensity is independent of the distance between the point and charge sheet. So we can write here the electric field intensity is independent of position of point in front of charge sheet. And what is the direction? If we will take a positive plate, the electric field intensity is away and normal to the plate. Okay. But if the plate is negatively charged body, negatively charged sheet, in that case electric field intensity is towards the plate. Okay. So electric field intensity is away and normal to the charged sheet. And for which item of charge? For positively charged plate. And vice versa. Vice versa means if the charge sheet is negative plate, then electric field intensity is towards the plate. So this is about the example 22.7. Let us discuss the example 22.8. Here we have to find electric field intensity between oppositely charged parallel conducting plate. Okay. So I have taken two charged plate. One is positive plate, another is negative plate, and their surface charge density are same. So what is surface charge density? Sigma. Here minus sigma. So I have to find electric field intensity at a 3 point. So this A point is left to this positive plate, C point is towards right of this negative plate, and B is in between these two oppositely charged plate. Okay. So we will apply which law? Gauss law. We will apply Gauss law. Now see, this B point is in front of this positive charged plate. So as per the previous example, what is the electric field intensity due to first plate at B point? It is positive plate. So electric field intensity is away from it. So this is, you say, this is the electric field intensity at which point? B point. Due to which plate? Positive plate. So what is electric field intensity at B point due to positive plate? It is sigma by 2 epsilon naught. And what is the direction? It is towards right. It is towards right. Okay. Now we will find the electric field intensity at B point due to negative plate. Since it is negative, the electric field intensity is always towards it. So what is the electric field intensity at B point due to negative plate? Let us say it is EB due to negative plate means minus. Then what is the electric field intensity at B due to negative plate? It is equal to same formula, that is sigma upon 2 epsilon naught. And since it is a negative plate, the electric field intensity is towards it. Okay. So actually how can you find? So to find electric field intensity, if I will keep a plus 1 charge here, so this plus 1 charge will be attracted towards the negative plate. So again the electric field intensity direction is towards right. So what is the net electric field intensity at B due to both positive and negative plate? Since both are in same direction, you just add algebraically. So that is sigma by 2 epsilon naught plus sigma by 2 epsilon naught, which is equal to sigma by epsilon naught. And what is the direction? Towards right. So that means electric field intensity in between two opposite charged plate formula is what? Sigma by epsilon naught. And it is in which direction? Towards right. that is from positive plate to negative plate, from positive to negative plate. Okay. Suppose I want to find the electric field intensity at the outside of this plate. Outside means which plate? Which point? A as well as C. So I want to find electric field intensity at A point. So this electric field intensity at A point due to positive plate is equal to what? This is the direction of electric field intensity at A due to positive plate, because electric field is always away. And for this negative plate, what is the electric field intensity at A? So it is towards the negative plate. So what is that value? Let us say EA minus. So I can say total electric field intensity at A is nothing but EA plus towards left and EA minus towards right. So if you take towards left is negative and towards right, let us say it is positive. But what is the value of EA plus due to positive charge plate? According to Gauss law, it is sigma upon 2 epsilon naught. Plus what is the electric field intensity at A point due to negative plate? It is also sigma by 2 epsilon naught. Okay. So if you add this, you will get 0. Similarly, that electric field intensity at C point is also 0, because for C point, what is the electric field intensity due to positive plate? So this is the direction. So this is EC plus. And what is the electric field intensity at C due to negative plate? Negative plate means towards it. So this is your EC minus. So both electric field intensity are equal and opposite. So net electric field intensity is 0. So this is actually, this example is actually, it is a parallel plate capacitor. So we will discuss in the later class what is a capacitor. In the capacitor, there are two oppositely charged plates separated by a small distance apart. And the electric field intensity in between two oppositely charged plates is always from positive plate to negative plate. Now see, this is just you take, in the previous case we had taken two oppositely charged plates. Then in this case we are taking similar charge plate. If this is positive, this is also positive plate. Due to these two positively charged plates, we have to find electric field intensity at A point, B point, C point. Okay. So first we will find electric field intensity at which point? A point. And you see, this is the positive charge plate. Due to positive charge plate, electric field intensity at A direction is away from the positive plate. This is the EA plus. Similarly, this is also positive plate. Due to this positive plate, you will get electric field intensity along same direction, that is EA plus. Then what is the total electric field intensity at A point due to two charged similar plate? Both are in same direction. So we can say electric field intensity at A is equal to EA plus EA plus. So that is equal to EA plus. What is the value? Sigma upon 2 epsilon naught. Here also sigma upon 2 epsilon naught. If you add this, you will get sigma by epsilon naught. And what is the direction? It is towards left. That is away from this plate. Similarly, if you will find the electric field intensity at C point, again it is electric field intensity at C due to first positive plate plus electric field intensity at C due to second positive plate. So what is the value? So since both are positive plate, the direction of electric field intensity for both are in same direction. So we will just simply algebraically add. So what is the value? Again sigma upon 2 pi epsilon naught, sigma upon 2 epsilon naught. We just add, that is sigma upon epsilon naught. And since it is in front of C and this is positive plate, this is positive plate, so net electric field intensity is towards right. Then what will happen to the electric field intensity in between these two plates, that is EB. So here the electric field intensity at B due to first positive plate direction is towards right. And for this plate, the electric field intensity is away from this plate. So both are equal and opposite. So what is the net electric field intensity? Net electric field intensity is that. So due to this, it is sigma by 2 epsilon naught, that is towards right, plus due to this electric field intensity is towards left, but value is the same, sigma upon 2 pi epsilon naught, but in left direction. So if you add, so both will be subtractive. So net electric field intensity will be 0. So this is the situation. But actually we are interested to take the electric field intensity due to oppositely charged plate. Okay, so this is example 22.11. Question is like this. This is a solid conductor. Okay, this is a solid spherical conductor with a cavity. So inside this there is nothing charged particle. So nothing charged particle means this is totally cavity. In this cavity at the center there is a minus 5 nanocoulomb. Clear? And this total solid charged sphere, the net charge on the solid sphere is equal to 7 nanocoulomb. Question is how much charge is on each surface, that is inner and outer of the conductor, how the charge will be distributed. Okay, now see, at the center there is a minus 5 nanocoulomb, and this is a solid conductor. This is a solid conductor. We know the electric field intensity inside a solid conductor is always equal to 0. We have already proved this. This is the statement. So now we will apply the Gauss law. So to apply the Gauss law, let us say I am taking an imaginary sphere of radius say r. Okay, so this is imaginary sphere. And this imaginary sphere I am taking the Gauss law. I am using, so I will apply the Gauss law. Okay. So to apply the Gauss law, we have to find what is the flux through this Gaussian sphere. So flux through the imaginary Gaussian sphere, that is imaginary surface, is nothing but E dot ds integration. And since it is a sphere, everywhere electric field intensity value is same. So the total flux through this Gaussian surface is nothing but E into area. But according to the Gauss law, the total surface is nothing but charge enclosed divided by epsilon naught. So here E into A is equal to, what is the charge enclosed by this Gaussian sphere? That is minus 5 nanocoulomb. So minus 5 nanocoulomb. Okay. So plus we don't know what is the charge within this sphere due to this solid conductor. Let us say it is Q dash. So divided by epsilon naught. So that implied, but electric field intensity inside the conductor I have told it is 0. So put 0 in place of E. So you will get 0. So 0 is equal to minus 5 nanocoulomb plus Q dash divided by epsilon naught. So from this we can say Q dash is equal to 5 nanocoulomb. Now we see this 5 nanocoulomb must be within this Gaussian sphere. Since we are discussing the electrostatic condition, charge is always distributed on the surface. Okay, so here this 5 nanocoulomb must be developed in this inner surface of this inner sphere. That means in this the total charge of what? 5 nanocoulomb will come in the inner surface of this inner sphere. So that the total charge will be plus 5 nanocoulomb minus 5 nanocoulomb, which is equal to 0. So, so we can say the charge inside this sphere or just above the cavity is equal to 5 nanocoulomb. But what is the total charge on this solid sphere? So you see, this is the total charge on this solid sphere. What is the value? 7 nanocoulomb. Out of 7 nanocoulomb, already 5 nanocoulomb is distributed on the inner side of the sphere. So the remaining charge, that is remaining charge means 7 nanocoulomb minus 5 nanocoulomb, which is equal to 2 nanocoulomb. So this 2 nanocoulomb will be distributed on the outer surface of this solid conductor. So this is the total, there is a plus 2 nanocoulomb. So that this 5 nanocoulomb in the inner surface and 2 nanocoulomb in the outer surface will give total charge of what? 7 nanocoulomb. So in this way charge will be distributed. So let us discuss exercise 22.22. Here you see the question is like this. A point charge of minus 2 microcoulomb is at the center of a spherical cavity. So this is a spherical cavity. Okay. So in the spherical cavity at the center, there is a minus 2 microcoulomb charge. And above this cavity, so this is the solid conductor, whose the volumetric charge density rho is given, how much? 7.35 into 10 power minus 4 coulomb per meter cube. So you have to find the electric field intensity inside the solid at a distance of 9.5 centimeter from the center of the cavity. So this is the center. So here we have to find, let us say this is a point P, which is what distance? That is R distance. So here R is equal to what? R is equal to 9.5 centimeter, which is equal to 9.5 into 10 to the minus 2 meter. And this cavity, spherical cavity radius is say R. So R is given 6.5 centimeter. 6.5 centimeter. Okay. So what we will find? We have to find the electric field intensity inside the solid conductor at what distance? At 9.5 centimeter from the center. So what we will apply? We will apply the Gauss law. Okay. So what is Gauss law? Gauss law, to find the Gauss law, I have to take a Gaussian sphere which is just touching to this P point. So with this R radius, I am drawing a Gaussian sphere. So this is my Gaussian sphere. So what is the flux? The total flux is nothing but the E into total surface area, because everywhere on this surface electric field intensity magnitude is constant. And what is the total area of the sphere? Let us say A. So E into A is equal to, according to the Gauss law, it is charge enclosed divided by epsilon naught. So we have to find what is the electric field intensity at this P point. So that implied E into area. So what is the area of a sphere? That is 4 pi r square, which is equal to charge enclosed by the epsilon naught. So what is the charge enclosed by the Gaussian sphere? So it is already there. A point charge is already there. What is that value? So that value is equal to minus 2 microcoulomb. That is minus 2 into 10 to the minus 6. So this is the charge, that is the point charge lying in the center. And we have to find what is the total charge within the solid. Okay. So how will you find? So rho is given. Rho is what? The volumetric charge density. Rho is what? Volumetric charge density. So we have to calculate what is the total volume of the solid within this Gaussian sphere. Then multiply rho, because rho is volumetric charge density, that is total charge per unit volume. Then what is the charge, total charge within this cylinder? So it is charge per unit volume into what is the volume of this solid. So volume is equal to, how will you find the volume? You first calculate the total volume, this is the total volume, minus volume of the cavity, then you will get volume within the cylinder. So we can write the value is equal to the total charge within this solid is equal to rho times into volume. What is the volume of a sphere? 4 by 3 pi r cube. So in the outer sphere, the volume is 4 by 3 pi r cube. In the inner sphere, volume is 4 by 3 pi r cube. So this is the total charge within this solid conductor. And there is a point charge of minus 2 microcoulomb. So this is the total charge within this Gaussian sphere divided by epsilon naught. Okay. So everything is given. Capital R, small r, epsilon naught you know, rho you know, everything is given. So you have to find electric field intensity. Just you calculate. So you see E into 4 pi, what is r square? R is equal to 9.5 10 to the power minus 2 whole square is equal to minus 2 into 10 to the power minus 6 plus rho. What is rho? rho is equal to 7.35 into 10 to the power minus 4 into 4 by 3 pi r cube. What is r? R is 9.5 into 10 to the power minus 2 whole cube minus small r 6.5 into 10 to the power minus 2 whole cube divided by epsilon naught. What is the value of epsilon naught? 8.854 10 to the power minus 12. So this calculation you have to take using calculator. So after calculation I got E is equal to minus 0.023 into 10 to the power 6 Newton per coulomb. Minus indicates the electric field intensity is towards this Gaussian surface. So that means this is the electric field intensity direction. At this P point, electric field intensity is towards the center. That is, or you can say electric field intensity is inward. Minus means electric field intensity is inward. Okay. So you see, this is exercise 22.15. Here, what is the question you see? There are two long uniform line charges are parallel. So you take two linear conductor, they are separated by 0.3 meter and each line has a linear charge density of lambda. So what is linear charge density? It is total charge distributed per unit length, that is called lambda. So here total charge per unit length, according to the question, it is given 5.20 microcoulomb per meter. This is the linear charge density of these two conductors. Okay. So we have to find what is the magnitude of the force. Magnitude of the force on the line charge on 0.05 meter section of other line charge. Suppose this is the first conductor, this is the second conductor. We have to find what is the force by this first conductor on this section. What is the length of this section? The length of the section is equal to what? 0.05 meter. So on this section, very small section, 0.05 meter of this linear conductor, we have to find what force will exert on this charge due to the first conductor. Okay, so we have to find that force. So what we'll do? We have to find what is the electric field intensity at A point due to the first linear conductor. So we can say electric field intensity due to first conductor on or at which point? At A point. So it is already discussed in the application of Gauss law. What is the electric field intensity due to a linear conductor? The formula is lambda divided by 2 pi epsilon naught into r. So which can be taken as just multiply 2 in numerator and 2 in denominator. So it will be 2 by lambda divided by 4 pi epsilon naught r. Why I multiplied? Because you know 1 by 4 pi epsilon naught we can apply, that is 9 into 10 to the power 9. So this is the electric field intensity at which point? At A point. Okay. So now you find out what is the charge on this small section. So charge on small section of length, how much? Of length 0.05 meter is equal to, you know what is lambda? Lambda is charge per unit length. Then what is the charge of this section whose length is 0.05? It is lambda into 0.05. So what is lambda here? Lambda is given what? 5.2 microcoulomb, that is 10 to the power minus 6 coulomb per meter into 0.05 meter. Just multiply this. I think you will get 0.26 into 10 to the power minus 6 coulomb. So this is the charge at this section. And what is the force? You know, if any charge particle will be brought inside an electric field, that charge particle will experience a force. So what is the force? force on charge at A is equal to F is equal to Q times E. So what is Q? Q is equal to 0.26 into 10 to the minus 6. What is E? E is equal to 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught is nothing but 9 into 10 to the power 9 into 2 into lambda. So what is lambda? Lambda is equal to 5.2 into 10 to the power minus 6 divided by R. What is R? R is equal to 0.3. Just calculate. You will get F is equal to, if you will calculate, I think it will come 0.0810 Newton. So this is the solution. So this is the last exercise problem, that is 22.17. Question is, how many excess electrons must be added to an isolated spherical conductor? You see, this is a isolated spherical conductor of radius 32 centimeter. So radius is equal to R. So R is given 32 centimeter, which is equal to 0.32 meter. So this is an isolated spherical conductor. No other conductors are present. Question is, how many excess electrons must be added to an isolated spherical conductor? So if you are adding some electron, that is charged particle, those charged particle will reside on the surface of the spherical conductor. We know for a spherical conductor, charge always lies on the surface. So here I have to add some electrons. Let us say n number of electrons I added to this isolated conductor. Then what is the charge of that isolated conductor? You know Q is equal to Ne. So this N we don't know, we have to calculate. And what is E? 1.6 10 to the power minus 19 coulomb. Okay, this is the charge. And so that if you add this amount of electron, that is n number of electrons, what will happen? The electric field intensity just outside to the surface is equal to 1150 Newton per coulomb. So that means electric field intensity just outside the surface means you take it is surface. So electric field intensity on the surface will be 1150 Newton per coulomb. Then what is the value of N? We know what is the formula of electric field intensity on the surface due to a charged spherical conductor. It is Q upon 4 pi epsilon naught radius square. So here Q is equal to what? Ne. Q is equal to N into E. E is equal to 1.6 10 to the minus 19 divided by 4 pi epsilon naught. So 1 by 4 pi epsilon naught is nothing but 9 into 10 to the power 9 divided by R square. What is R? R is 0.32 square. So this is the electric field intensity on the surface. But as per the question, what is the electric field intensity just outside to the surface given? 1150. So everything is in SI system. So we will find the value of N. So if you will calculate N using calculator, you will get 2.04 into 10 to the power 10. So this is the answer. So this amount of electron must be added to this isolated spherical conductor so that electric field intensity just on the surface or just outside to the surface will be 1150. So this is the answer. So with this, I am concluding the today's video lecture, that is lecture number 4 of chapter 22. So I finished the Gauss law, and in the coming class we will discuss the electric potential. So okay, bye.